Hi everybody, so we're finishing this chapter 9, or hopefully at least we move as much as we can on it. There will be also a quiz on it. I did not really honestly decide if it's going to be a participation quiz similar to the last one we did on chapter 8 or a full-fledged quiz like the one for chapter 7. So once that's determined, most likely tonight I will I will let you guys know, and I will give you ample of time to basically prepare one or the other. It should be fine. I think that's one thing that we have to do. So we have a lot of people who are not here for some reason or the other, and that's what happened actually with the last quiz, because people missed on the things that are happening and they missed it, so that's really not good. So I guess I can only do so much because I send reminders, I send stuff in between. So people are busy, and that's part of life, especially now in this confinement thing that we're sitting at home. Anyway, so let's continue with the topic. Any questions before I start? No? Okay. So here where we were last time, basically we discussed the beginning, basically the missions to the moon, especially Apollo's missions and what we learned at that time and the general properties of the moon and so on and so forth. Now we're talking about the surface of the moon. So this is a continuation of the topic that we're talking about in chapter 9. And the geology, of course, of the moon, we talked about it. It doesn't have much geology going on right now. It may have had it in the beginning, but not right now. And we'll talk more about the surface. And the surface is characterized by a lot of impacts, basically, on it. So a lot of craters, indicating actually the fact that there was not much going on in terms of resurfacing, in terms of geology or anything like that. So that's basically some of the things that we know as far as the surface. So the biggest feature of the surface of the moon is its craters, okay? And so this is some of the, of course, one of the things that we know, at least looking at it from the Earth, is the fact that the moon is tightly locked with the Earth, so we can only see one side to it, because as it's rotating around the Earth, as it's going around the Earth, it's also spinning, revolving around its own axis, and it's the same period with which it goes around and turns. So every time it moves, it's always giving us the same side, because it's spinning with the same rotation. So that's basically one of the things that we know about it. So the surface that we look at has so many features on it, basically. It has, at least up front, if you go tonight and look at it, and it's going to be a bright night. I think it's going to be the full moon in this next few days at least. So and I know also something else that I didn't talk about last time when we met, and that is the project. So don't forget that you have observations for the moon this week too. Now, a question from one of you guys, apparently she missed one day. If you missed one day, please mark it as an X. You don't have to restart all over again or something like that. Just mark that. And that's it. I mean, mark the observations for those few days and then move on and do your next observations, which is this week. So I don't want you to fall behind. Besides, and I cannot really extend this one because I want to collect them immediately and post their grades so that you have all of them. If you start new one next month, it's going to be over after the after the school is over. So I will not be able to grade that. Anyway, so don't forget we have observations, and we should be sometime in the next few days or so full moon. So that's a good opportunity to look at the moon and see some of its features. I think we are cloudless. And this is the thing that we look at when we looked at it. So it looks like there are some dark spots on it and some bright spots on it. And people in the old days thought, hey, this must be some sort of oceans on its surface, and maybe mountains or features other than that. And the belief was that this is a watery world because of those features when they looked at it with the naked eye. Of course, now we know that there is no water, at least in the liquid form, on the moon. But and they gave them names. They gave them names that basically call them like mare, which is French, at least the Latin word for like a lake, or I guess a pond or something like that. So that's basically, and the plural of that is Maria. So basic Maria. So basically that's the features, and they gave them names because they are big features that you can see them. Now we know actually they are not actually water, but rather after those impacts formed on the moon, after the moon was impacted with some bombardment from outside, apparently magma, or at least lava, flowed to the surface and basically made those features that they look like shiny and reflecting and dark at some point. And as a matter of fact, since they're dark, indicating that they're made out of metal, so that's their metallic structure in there. So that's some of the stuff that we know, at least in terms of the face that is the side of the moon that is facing us all the time. The moon rotates and spins around its axis and all the time. So if we're looking at one side of the moon, the other side is on the other side, but because it spins as it's moving, all of its sides will see the moon one time or the other. And the day, of course, on the moon is equal to its month, which is about 30 days or days. Okay. So it's dominated, the feature of the moon is dominated by basically craters and impacts that, or the remnants of that. And because of those impacts, they basically shatter the surface of the moon or the rocks of the moon, and they fly in the sky, and then, not in the sky, it doesn't have atmosphere. So for a short while, there is some atmosphere, and then they fall back, and they fall back in the form of dust. So the surface of the moon has a layer of basically that fallouts that is more like a sand, fine structure, basically dirt, and that is basically the main feature also when you are there. And we will see pictures from when Neil Armstrong and Buzz Aldrin basically walked on the moon, and you will see the imprints that they left as their feet basically sinks to the surface of the moon, because of that fine structure on its surface. So again, this is the moon surface, consists about 17% of those mareas and 83% of the rest, which is all of it cratered basically. And the fact that you have an impact in here indicating that this impact happened later in time than the actual when the surface was formed in here. So we're going to talk about that. We're going to talk also about how we use this ones to this technique, the cratering technique, to date surfaces and basically at least the upper layer of a planet, if in case we have access to that. The moon's rocks, basically, this is one of the rocks that were that was brought in here, and this has porous structure, indicating that it was formed in some sort of a, this is a basaltic of course, rock, indicating that it was actually formed in a lava. So that's basically what this the main features of the moon. Again, this is one of the youngest of the large lunar impacts, and this happened about 3.8 billion years ago. So apparently the moon, and this is one of the things that we're going to learn also, is that it went through a very, very, very active, highly, basically, high rate of bombardment, and then after that it subsided to the normal rate. Now, was that unique to the moon? We don't think so. Actually, that same thing happened everywhere in the solar system. Immediately after the solar system was formed, there was a lot of debris in the solar system, and that was kicked out by the big planets, and the small planets alike contracted and pushed around and so on and so forth. And some of it fell back on whatever surface it can find, and the moon was one of them, and the Earth is another. So the reason why we don't see them actually that much on the Earth is because of the fact that the Earth has resurfacing due to the geological activities on its surface. So this is the imprint I was talking about from Neil Armstrong, actually. And again, this is the boot, and actually was talking about the dust that he can see in there. It's so dusty, the surface in there, and the dust got everywhere in their on their suits and so on and so forth. And this is the imprint that was left in there, indicating that the surface has a sand-like structure, which is a fine, and it's just because of those impacts that basically broke down the surface of the moon over time, and that's basically the buildup of that is what we see. So This is basically the next section. The idea here is the following. When people, of course, were looking at those impacts on the moon, initially they thought that there must be some sort of volcanoes, because that's what volcanoes do on Earth. They look like that's how they look like. It was actually Gilbert in 1890 from the USGS who suggested that maybe there is something flawed in this argument based on the mountains. And they are first of all circular, and the area in there higher than at least the edges of the circle are higher than both the crater itself and the outside, indicating that there is something wrong in here about this picture. This is not how at least craters are formed on Earth due to the volcanoes. So, and that idea later on was confirmed, and the fact is that actually they are coming from outside. This is not from the surface of the moon basically making volcanoes, because this is how this would look like. Whereas in here there is this small impact, and then there is this distribution which is consistent with an impact, a high velocity impact that can form that structure. So this is what the lunar impact was, and of course his argument held true later on by observations basically and more experimentations and so on and so forth. So how does the craters form? Here is the process through which craters form. So you have an object that is coming super fast. Remember that in order for an object to escape any planet, it needs what is called an escape velocity. An escape velocity, if you're moving less than the escape velocity, you will not be able to leave the pull of the gravity of that planet. On Earth, any object that is moving faster than or equal to 11.2 kilometers per second can escape it, can escape the pull of the gravity of the Earth. They're actually going to go forever and ever, supposedly not to return to Earth at all. That's the idea behind the escape velocity, and it has to do basically with the gravity, the pull of the gravity that is inversely proportional to the square of the distance, but also proportional to the mass of the object. Now, the moon has also gravity, albeit it's smaller and has also smaller radius, but its escape velocity is a lot less than that of the Earth. It's only about 2.4 kilometers per second. So an object that hits the surface of the Earth, even if it was not moving at all, must be moving at least at the point of impact 11.2 kilometers per second. Because it's going to, the reason why you can escape the pull of a gravity and go to infinity is because while you are here, you have potential energy. In order for you to while you are here, you have potential energy higher, because remember the distance in here. When you get closer, you lose that potential energy. In order for me to take you from this point that you don't have much potential energy to this point that you have a lot of potential energy, I have to provide you with kinetic energy basically to do that. In other words, I have to push the object further up. Now, if this object now has this much potential energy, if it comes back, it's going to release it back to the Earth. That's why the escape velocity is the minimum velocity of impact. So if you see in tomorrow a crater somewhere, you know that at least it hit the Earth with this much velocity. So you can imagine how much force it's going to provide, because all you have to do is multiply the mass times the velocity, that's the momentum, and assuming that it was not moving, that is the impulse. So you can find basically the force of impact if you can use that. And now, an object that hits the Earth must have been traveling before, so the velocity can be actually greater than 11.2 kilometers per second. Now, if we're talking about the moon, actually the minimum impact velocity will be 2.4 kilometers per second. So this is the minimum velocity with which you're going to hit the moon, and probably more. 2.4 kilometers doesn't sound much, but remember, this is per second. So in an hour, you're going to multiply that by 3,600. So this thing is moving about 12,000 kilometers per hour. So this is super fast. You cannot catch it with your car or anything like that. Your car at best is going to do what? Probably 200 kilometers per hour. That is a racing car or something like that. So this is 12,000 kilometers per hour. And imagine a rock that is so big. So it's going to have a tremendous impact. So the first thing that you're going to have is an impact, and that impact is going to occur on the surface of the moon, or the object in the case of the Earth. Then you will have the shock waves that develop because of that high impact. There will be shock waves that develop on the surface, and debris starts to fly all over, basically, and the object itself breaks into pieces, okay, and then takes from the materials of the inside. Now, ejecta are thrown out of the material. Basically, the debris and all of the stuff that comes out basically comes out of it. So in this experiment, you can conduct it basically with small impact object. Basically, take a rock and throw it on the surface of sand, fine sand, very fine sand, and you will see the same structure forming. So this we can do actually ourselves. We don't have to imagine it, because it's simply you can do that. And then after that, the material settles back on the surface. So this is basically how craters are formed. Okay, so it's a 4-step process. The first one, and that depends on the velocity, by the way, is the velocity that hits the impacts. Then that is that shock waves and the destruction of the materials. They fly all over the place, and basically that's and when they settle, that's the crater that remains at the end of the day. Now, studies have shown that the diameter of this crater is directly proportional to the size of the impacting rock, basically, that formed it, or the impacting meteorite that formed. So that's basically the bigger they are, the wider they are. The bigger they are, the more the diameter of this region is. So, and this is one of this crater impacts. I mean, it looks like it's coming out, but this is actually a picture of an impact that is 75 kilometers in diameter. So the distance from here to here, it's about 75 kilometers. Okay, this is the point of impact probably, and it has this circular structure, indicating that this is actually a crater. That's really why there is a symmetry in here. Now, like I said before, the moon actually is going to be full moon in the next few days. I hope you guys will have some time to go out and first of all do what you're supposed to be doing on your project to indicate where you saw it and how it looked like. And so this is basically how it looks like. This is on a full moon. This is on a different phase of the moon. And of course, all of this is the light reflecting from the surface of the moon, and reflecting from the sun on the surface of the moon, and you see all of these features, including in here some of those ejecta materials that you see from the different impacts that hit the surface of the moon. Again, this is the features that we can see with our own unaided eyes, and with the telescope, it's even better. You can see far more details in the moon. So I leave it to you guys so that you do this one. This is due this week, so hopefully you're going to go and do that, and I don't see any problems in terms of forecasts or anything like that. On a full moon, which is in the next few days, the moon should appear super bright, okay? And you'll be thinking that maybe it's so bright as anything else, and it is compared from our vantage point on the Earth. But actually, the Earth, if we're sitting on the moon, would look even brighter, because the moon actually is made mainly of rocks, as we talked about earlier. It's silicate structure, but the Earth has this upper layers, which is an atmosphere and also the clouds, and will make it far more reflective. And actually, the Earth will be even shine more bright than the moon does. So this is a side-by-side picture of both the brightness of the moon and that of the Earth, if we're looking to them at distance from somewhere. Okay, that the moon will appear less bright than that of the Earth, and both of them are actually reflecting light from the sun. Now, we use craters to count basically and date the surface of a given planet. Of course, these things happen over a long time. This is an example from Meteor Crater in northern Arizona near Highway 40. And basically, the thing with this is you cannot really, because one of the way is that, okay, you look at the surface, for example, the moon or that of Mercury, and you see a bunch of craters on its surface. And you say, okay, when was it the last time the surface has been basically resurfaced, or when was it the last time? So you can tell the age and the activity on the moon, on the surface, by just counting how many craters it has. If it has a lot, it must be old. If it has a few, then it must have changed itself to a point where the old ones are gone, and now the new ones are the only ones exposed basically to the late hits. So, and if it has none, that means the surface is completely brand new, because if it has none, that means whatever impacts that happened in the past few thousand years, they're all basically gone. So that's how, what we talk when we say, well, that's what we mean when we say we're using it to date the surface of a planet, is basically to count and see how many they are. And if we see a lot, that means the surface is very old. If we see few, that means it's very, very new. It means indication that there is some geology on underneath that changes the surface so much to the point that you don't find many. Like, for example, the case of the Earth. Now, how do we know that? How can we tell just by this number? Because we must have had some understanding of these things. Of course, we can't rely on observations to see, for example, hey, today there was a crater. Is there going to be another one tomorrow? Is there going to be another impact 2 days from now, 3 days from now, a year from now, 10 years from now? It's not on our human scale at all. It's in the thousands of years. So we can't rely on that. There's other alternatives that we use. One of them is actually the moon itself. The surface of the moon became a standard with which we count the craters and indicating the age of a given surface, especially since we were able to actually date the surface using different techniques, radioactive techniques, then we should be able to tell using that. So it's a valuable piece of data that allowed us to basically trace the history, not just of the moon, but use that as our gauge, basically, to use it for other objects. Now, if we look at the surface of a given moon or given a planet in the solar system, then we can decide. We can say, oh, as compared to the moon, this must be this much old, okay, or this much young. Then the other also technique uses the possible impactors. Those are the asteroids that or objects that move in the sky that potentially can impact the surface, and estimated based on doing statistics and analysis, and that comes up with a rate. Again, those two, they're compatible. The two observations seem to confirm one another, that this is actually a valuable technique, whether this one or the other. So that gave us confidence in the first set of data to use it actually as a technique to date basically surfaces, just by able to count the number of craters. So we have strong evidence that the technique is actually valuable. It's working. So this is what happened then when we took that and studied the craters, for example, on the moon, that apparently at some point there was a high number called of impacts called the heavy bombardment periods. This is a time when there was a lot of materials in. This is immediately after the solar system formed. Remember, the solar system formed on the planet Earth at least about 4.4 to 4.5 billion or 4.6 billion years ago. So that's immediately after the sun basically formed. Then the planets started to coalesce and form, and then they basically when the sun basically formed, then expelled most of the materials in the solar system. But there were some heavier elements, heavier objects that remained, and those heavier objects, they basically stayed in there until a planet comes in, sweeps by, basically moves, attracts some, moves others in other directions, and there was some chaotic behavior during that time. The moon surface and actually the Earth and everything in the solar system was subject to a tremendous amount of activity in terms of bombardment. So this is what we know. This is the surface, the last basically feature in terms of the Mare, called the Oriental. That is the one that has a little bit of lava that came out. Its features are still looking like they were immediately after the impact, but the others that happened before that, that is when the lava flowed on the surface of the moon. And then after that, this activity subsides. It's not zero, it's continuous. As of today, we know that there is a rate But this is the time scale in here is not in years. This is in billions of years in the past, basically. So one in here is not 1 year, it's a billions of years, but the rate at which is constant, basically. So this is how much we're receiving on a regular basis. So that's basically the studies and how useful they are in determining the age of the specific surface based on the number of craters that it has. Okay. Now, the moon itself, we wanted to understand where the moon came from, because the fact that the Earth has this moon is an odd thing, actually. And that puzzled scientists and astronomers for a long time, and they tried to understand where did the moon come from. So there were several possibilities that people started to explore and try to see what kind of arguments in or against. And one of the theories is that the moon and the Earth, they were probably bigger planets, and somehow it split into two pieces. The bigger piece ended up being Earth, and the other piece started spinning around the center of mass where the two existed. So if they were here, when they separated, most likely the center of mass is actually very close from the center of the Earth, and that is actually the point where which right now we don't see it, but the Earth actually itself is being impacted by the moon as much as the moon is being impacted by the Earth. So there are some arguments for this one, and the biggest one is that when we looked at the rocks of the moon, we saw that there is some similarity in terms of their history with the Earth and things like that, especially in terms of radioactive materials. So there were some arguments for this one. But there was some also problems with this theory, and one of them is, for example, the density and the lack of minerals and things like that. So there were some problems also with this one. The sister theory actually states that basically, hey, maybe the moon and the Earth, they were formed together as two planets, but because the Earth is much bigger than the moon, the other planet, namely the moon now, was forced to spin around the Earth. So that's basically another hypothesis that was going on. That was actually has a weaker argument for it because of the fact that similarity in the structure, so they could not have formed independently of one another. And the same thing goes for the capturing of the moon, similar to what happened, for example, of how how Mars ended up with two moons. It captured them from elsewhere. That too is kind of weak. So the arguments for the idea number one and the last one are actually stronger. So the last theory actually is the following. Basically, a giant impact from a planet-sized planet-sized object called Theia, actually the size of Mars, actually, must have hit the Earth at the specific angle. And that explains a lot of things. First of all, the tilt of the axis of the Earth. The fact that the Earth is tilted 23.5 degrees could be implied with this impact that is just enough to do that tilt. So it's not full-blown hit. If it was that, then the object will scatter, and probably both of them, and then the Earth probably will form later on, or the two objects will coalesce into one big object or something like that. So it was at an angle just enough so that the materials are scattered, and the bulk of this Theia, or at least a good portion of it, stayed somehow intact. I was going to simulate that, and probably I will simulate that on Universe Sandbox next time when we meet. So I'll take an Earth-sized object and I take a Mars basically object and bring it to one another and see what the impact, and if we can reproduce that, if we can actually do that on our own, take the Earth and hit it with Mars at a specific angle and see. And of course, we have to accelerate time. We're not going to wait billions of years. That's not possible. We're going to accelerate time and see if indeed, actually, that's what we'll end up with initially, of course, there will be scattered materials all over the place, but then gravity will start to put materials together, and that's going to form, for some time at least, the Earth had probably a ring of materials going around it because of that impact, and then it formed that. So the tilt of the axis of the Earth can be explained in terms of that. Also, the similarity in terms of structure, and the dissimilarity also in the structure, in terms of the structure, because hey, you have different objects that hit the Earth, so they are not exactly similar. They are not exactly opposite to one another. So it explains a lot of things. So the giant impact hypothesis is actually the strongest right now that we're going by. And this tilt, of course, has tremendous implications on life of the Earth. So if this is true, then actually it's the moon that caused the life to be possible on Earth, because if there were no seasons, there was no life, there was no nothing in here. So besides the fact that the moon has influence on the tides, as we talked about in chapter 8, so it seems like the moon has played a major role in terms of making life possible on Earth. So if the moon was not there, it would have been very, very hard to have an Earth the way it's supposed to be right now. Right now, I'm missing a lot of people. I'm just looking at the number in here. So I'm going to take the attendance hopefully around maybe 3 o'clock or something like that, just before if I forgot or something. So that's basically everything that we're supposed to talk about in terms of the moon, and in terms of its history, in terms of its surface, in terms of the flights that we went to. And this is one of the two cratered worlds that basically are talked about in this chapter. So the next one is Mercury. So Mercury is, of course, a planet. It's not a moon. And we will see that its surface is very similar to that of the moon in terms of the craters. So that's part of the Mariner's mission when it went there in 1974. It took a lot of pictures when it did its flyby near Mercury. So we learned a lot about how it looks like and things like that. So that's the other cratered world in this chapter. So this chapter is divided into 2 points. First of all, the moon, and the second is Mercury. We're going to talk about its composition. It's going to be different than that of the moon. Remember, the density was our guideline in terms of how it's made up, in terms of its materials and so on and so forth. And one of the things that we thought was true for a long time for Mercury, and that is it was tidally locked with the sun, meaning similar to how the Earth is. Remember with the moon as it goes around the Earth, it also rotates around its axis with the same time. So if it does 30 days, for example, to go around the Earth once, it also does 30 days to rotate around its axis, giving us all the time the same side. This is what we thought, at least for a long time, until recent studies, actually in the 1960s, confirmed that that's not true. So we're going to talk about the fact that actually Mercury itself has a spin that is different than its period, than how long it takes to go around the sun. Okay, and then we'll talk about its topography and basically how this thing evolved. So its structure. First of all, the big picture. Mercury has a huge core. It's the size of the moon, actually. So it's, for all practical purposes, it's a core, and with a little bit of a few hundred miles only of non-core structure. So this is one of its main features, which prompted some recent studies, actually, that was published in last year, I think. No, actually, it was published in 2020. That suggests maybe Mercury itself was not the way it looks right now at all. It was actually a giant planet similar to what Jupiter is. And what we're looking at is whatever is left from that basically planet. There was a problem with this theory. Of course, not the size of Jupiter, but it was a gas giant that ventured toward the close by. It was captured by the sun, and that's basically how it looks like. There were some problems with this theory, actually. The fact that if it was a gas giant, at least from our Kepler observations for the exoplanets, these giants, they retain their atmosphere even if they're near the star. So what happened to here? And why did it lose it so fast? So there were some studies that was conducted, and actually there was some documentation to support it. But there are a lot of criticism for these studies for this reason. So the current understanding is that it formed similar to how the Earth and the other planets did. Granted, because it was very close from the sun, it probably lost most of its materials, and much faster than anything else. Of course, the atmosphere, whatever little it has right now, and that's basically what we're looking at now. It's settling down faster, and it's basically this is how what we see it. It's much smaller than the Earth, for example. It's 1/8 the mass of the Earth in terms of size. Its density is 5.4. It's very close. It's the second one after the Earth, but it's much denser than the Moon, for example, indicating that its structure is more metallic than the Moon was, because the Moon, we said that it's more silicate, more basically how should I put it, more a rocky than rock than metal, whereas this one is more metallic than the moon. One of its characteristics, of course, it takes 88 days to go once around the moon. So by the time a year has passed, it would have gone for what? For almost 3 times and something around the moon, around the sun. I'm sorry. So it's 88 days. Its cycle around the sun. One of the problems that really puzzled scientists also for a long time, astronomers, and that is the revolution itself, or the motion itself. It's not like any other planets that we know of. For some reason, it precesses around the sun. It goes around, okay? So it's like a top, basically. And so if this is one of its cycles, so it's going to go like this and then return back to it. And there was a problem. Astronomers for a long time thought that maybe that's the influence of Jupiter. So they recalculated the path of Mercury based on the influence of Jupiter, and they found some corrections. So maybe Jupiter was not enough. So they had to include more like, Saturn, because that's the next big player after Jupiter. And that did not count for it fully. So there was a puzzle for a long time that this precession, this motion of Mercury around the sun was not fully understood. And took the theory of Albert Einstein in 1908, the general theory of relativity, that basically explained and solved this puzzle that because it's so close from the sun and the sun has a huge mass, the sun actually has deformed the space-time continuum, and that explains the motion of not just, of course, Mercury, but all of the planets and the entire thing. But the reason why we couldn't see those corrections, they're not so obvious, at least for Venus and the rest of the planets, is because they're far away, and the deformation in the space-time continuum is so small that you don't see this effect. But for Mercury, because it's very close from the sun, that the relativistic effects need to be taken into account. So there is a precession that cannot be explained by Newton's theory. That's one of the things that basically shatters what we know in terms of the classical mechanics, the motion of Mercury around the sun. So that's one of the things that we know. So it's 0.39 astronomical units from the sun. So if the Earth is this much, this is about slightly less than halfway. So if this is the distance, slightly less than halfway, 0.4, 40% basically of the distance from the sun. Granted, this is the sun. This is the Earth, for example. You go to about quarter distance, so that's how it is. Remember, those two numbers, they match Kepler's laws. The closer you are, the faster the object moves. Remember the expression that relates both the period squared and the distance cubed. Because the distance is smaller, the period now must be less. That's the time it goes once around the sun. One of the peculiar properties of this planet is its eccentricity. It's so eccentric compared to, for example, Earth. The Earth is 0.0167 or something. This is much bigger, so it's much more eccentric. So at some point, it's very far away from the sun, as much as 70 million kilometers, versus very close at some point when it's near point of 46 million kilometers, the so-called perihelion and the aphelion. So this is some of the big picture in terms of the planet Mercury, in terms of its big characteristics. In terms of its size, it's of course much smaller than the Earth. I showed you last time the numbers, and that's basically one of the things that characterizes this planet. It's the smallest planet in terms of size, and it's the one that is the closest from the sun. When you look at it at night, it always follows the sunset or comes before sunup. Usually it's around the sun's position because, again, it's very close from it. Now, how do we know it's not spinning, or at least how fast it goes around its axis? So what we do, we send a radar. This is solar system astronomy, so we can use radar, basically. Send a radar, send a signal, and see how the signal comes back. If the signal comes in changed, then hey, you know the object is not moving. The object is stationary. Now, if the signal moves one way, Let's say, for example, this is frequency and this is high and this is low. So if that's the case, if it shifts toward the high, that means it's coming toward you. Yes, if this is high. So if this number was a higher number, let's say, for example, the frequency that you sent it is, I don't know, some gigahertz, and now it has increased in value. In other words, the wavelengths has shrunk, okay? Then in this case, you say, oh, that object is coming and it's coming fast, okay? And you can determine its speed based on how much shift there is. If it shifts toward this side, now it's moving away from you. So if the frequency is getting less and less, in other words, the wavelength is getting longer and longer, then in this case, you say, oh, that object is moving away from me, okay? And you can determine the speed based on how much shift there is. Now, if it comes both, now it has shifted both on this side and that side, then this object is in the same coming and leaving. It's coming towards you and it's moving away. Coming towards you, how do you know that? Is because it's shifting toward lower frequencies. Going away from you because it's shifting toward higher frequencies. So this must be spinning. One side is coming to you and one side is receding from you. So this one will broaden the spectrum one way, and this will broaden it in the other. So the one that is receding from you will make this frequency move this way, and the one that is coming toward you will make the frequency higher. So that's how you interpret the signal of a laser beam that you send and hit an object that is spinning. Like I said, if it was not spinning, you should see the shift one way or the other, or no shift at all. If it's no shift, it's stationary with respect to you. So if you're moving, it's moving with you, basically. Or if it's coming towards you or moving away from you, the whole signal intact will move one way or the other. But in here, the signal did not move one way or the intact. It's tatter. It increased on both sides. It moved this way and in the other way in the same time, indicating that this object actually in the same time coming and leaving. I mean, coming towards you and receding from you. And that is the only way we can explain this one, is that by the fact that it is spinning. Now, how fast it spins is how broad it is. If it is too broad, that means it's spinning so fast that there is a high shift one way and a high shift to the other side. That's basically how we can determine. We can determine actually the exact speed. This is what we learned, that it's actually spinning when we hit Mercury with it at the rate of 59 days. It goes once around itself, 59 days. This is the day on Mercury. So if you sit there, it takes almost 2 months from our own months for 1 day on Mercury. Whereas it takes 88 days, almost 3 months, for a whole year to go by. So a day there is a little less than 2/3 of a year. So imagine that, almost what, take 3 days. They make 3 days, and on Mercury they make 2 years, basically, on it. So you see how the numbers are? See what they mean? They tell you a lot. So this one thing that excluded something that we thought was the case between the Sun and the Mercury, and the fact that they were tidal locked, they were not. Because if they are, these two numbers must be the same. Like, for example, the case of the Earth and the Moon. They are not. They are different. So that's one thing that we know about this one. So this is in terms of its at least rotation. This is the rotation and revolution of this planet. So it's really something that we have to take that into account. Also, the other fact that we know in terms of its surface is the temperature. The temperature changes a lot, anywhere between 100 Kelvin at night to 700 Kelvin midday. Remember, a day takes a long time to go. It's 30 days, basically. 30 days basking in this high temperatures, and 30 days basically at a much, much lower temperature below freezing on Earth. This is in Kelvin, though. So 100 Kelvin is about negative 170 degrees Celsius. I don't know how much it is in Fahrenheit. Probably it's negative 120 or so. So it's super cold, okay? And the high temperature, 700 Kelvin, which is about 430 degrees Celsius, that is also super hot. So, and that is actually melts a lot of the materials in here. You cannot stand that temperature. Nothing can stand on it. So it's super hot because of the fact that it's very close from the sun. That's how we know that. And because also it doesn't have an atmosphere. So it doesn't have any kind of a greenhouse effect to regulate a little bit its temperature. This planet has the highest gradient, the highest difference in temperature between day and night in the entire solar system. There is a gap of 600 Kelvin between the min and the minimum and the high temperature. So that is something too much of a stress on anything, okay? Including its own surface, by the way, because of this difference in temperature will cause the surface to crack and start to basically give up under thermal stresses. So thermal stress is a big factor in here. Of course, the entire planet is rigid, so we're not too worried about it. But at least specific points, specific rocks, they should really be under a lot of this stresses in here. So this is about 600 Kelvin or 600 degrees Celsius. You pick your choice. I don't know how much it is in Fahrenheit. 430 degrees Celsius must be some probably 600. I don't know. I'm just putting them. I probably should use a calculator to find what that temperature is. But the point being in here, the standard temperature that we use, actually the unit, the scientific unit is Kelvin. Okay? Any questions so far? I need to take the attendance. I promised I would take it, so I need to take it before I forgot. I know that somebody else came in after I said that. So usually what I do is take a snapshot of my screen, and basically since I know most of your nicknames by now, I use that to mark the attendance on my book. Okay, so let's continue now. So in terms of its topography, or at least its surface, basically, like I said, in 1974, there was a flyby by Mariner, which it took about 2,000 pictures and revealed that it has a surface that is basically looks more like the moon itself because of the different craters and the impacts that it has on it. So whatever happened to Mercury, it happened a long time ago. There was actually no criticism of that studies. So this has happened a long time ago, over 4 billion years ago. So it cannot have, it could not have had a big atmosphere. Otherwise, the surface would not have appeared like that of the moon. It's not exactly identical, but if you look at pictures and you put them side by side, you probably wouldn't tell the difference until somebody tells the moon this is Mercury. So that's really some of the things that we know in terms of its surface. And this is actually an actual picture. This is an actual picture. It's not as much as the moon they were, so indicating that somehow maybe there was some geology early on, but it's still, there is a lot of impacts in here, including this big, basically, crater in here, and where the other small ones that formed after it. So you can always tell the age from just looking at them. One of the big features in on Mercury is this long cliff. This is 1 kilometer high. This is basically, there is a big shift somehow that happened on the surface of Mercury itself, and this is a more recent one. This is not an old one actually, because as you can clearly see, this is on the craters. It goes through all of them, indicating that this is a recent activity on the surface. So which means that this thing probably is still readjusting. The surface itself is still kind of active, not kind of plate tectonics or any kind of something like that. But that's, of course, this is a long time ago. This is in the thousands of years when this has happened, because there is more craters in there that are younger than this. Okay. This is the entire chapter. I promise you guys that we will be able to finish it. So I'm going to be working on the quiz for this chapter. Like I said, I didn't decide 100%, although I am leaning more toward the format that we did for chapter 7. Which means that this Thursday, you guys need to have, you will be given a little bit more time than last time when I did chapter 7. The reason why I'm saying that is because for some reason, a lot of you guys are not taking, I mean, they're relying on the uploads that I upload to YouTube. And I had a tremendous issue with my computer recently. It's not charging actually. And if I download something, it takes forever for me to work on it. So I'm not going to be able to probably upload this one. I'll do my best. But I will put an announcement on Canvas. I will put probably the PowerPoints also on Canvas. And hopefully people will take this more seriously than what happened last time. And I will give more time for you guys to do the quiz. So I'm hoping that this Thursday you guys also will spend it making sure that these things are sinking in before we move on to other chapters. We still have a long time to finish before we finish the course, so we want to make sure that these things are on time. Any questions related to this or the project? Yeah, the moon project, the moon is still due on time. Okay, I did not change that. So if it's the 21st, it's the 21st. And you have the report form itself. Let me look at it to make sure that you guys have it, because I don't want to. There was a question regarding the grades. I did not upgrade the grades, so please don't pay too close attention. I plan on doing that after I have finals the next week or so for about 3 of my other classes. So I plan on updating yours immediately after that, after those busy times next week and the week after. So after the next 2 weeks, I should be able to update all of the grades in terms of your class. And by then, we would be readying ourselves also for other exams in here. So most of the exams in here are going to be automatically graded, so I'm not too worried about that. But there was some issue with the averaging, basically. Okay, this assignment is taking as much as this assignment, whereas this one is just a participation quiz. So I need to work out the formula so that you reflect better your average, so that you will have a more understanding of what's going on. So please bear with me for another 2 weeks after at least I write all of the exams for the other classes, and then I have those for you. And let me go and look at the project for the moon. Lunar observation project. It's due the 21st. And 21st is, what day is that? What day of the week that is? 21st is Thursday. So, you know what? I'm going to do something in here for you guys for the project, okay? To help you out on it. Although, not really much other than... I'll see if I can change the lab report, the activity report, to make it a little bit more, much easier for you guys to write than having to, with a spell checker and all of that, to make it easier for you guys to do, okay? So I will try to have that, and doing so, it's going to expedite the report itself, because right now you have to print it and do that. Do you guys think the 21st, because it happens, the last observation as far as the project is concerned, is supposed to happen on, actually it's on Canvas, I'm sorry. It's on the syllabus. So May 14th is your last one. After that, so the observation, you have one on May 7th, and then another one on May 14th. And then after that, you have a week basically to turn your project. Does this sound reasonable time? 1 week after your last observation? Okay. So we will keep it then the way it is on May 21st. So that's when it's due. Please do ask, make sure you're doing it right, okay? I really want it to be a learning experience. I don't want you guys to feel like you're doing something automatic and just dropping it, and later on, okay, I got a grade for it and I have no idea what I did. No, I want you to really take full advantage of these projects, because I think I personally value them more than a lot of the things we do. I know that the exams are also teaching moments. I know a lot of things that sometimes we do that they can be powerful, but the projects by themselves, especially if you have a chance to work with somebody, albeit remotely, are much better than having to than a lot of other things. So please do ask questions and make sure you do them right. If you guys don't have any questions, I don't want to start a new chapter, honestly, until I figure out exactly what I'm going to do in terms of exams for this one. And if we do start another one, we're going to be just 2 ahead of where we need to be. Okay? If not, see you guys Thursday. Okay, if the moon is directly above me but a compass, okay? Just put it, okay? Ah, the compass shows south. Okay, just put it, describe what it is, okay? This is not an exact thing, okay? And state what you just said. Okay, Andrew? Put it exactly in the way you said it. That's actually perfect. Okay, guys, see you Thursday.